All right, just a heads up. Last night, my sinuses exploded, so just in time for the talk, so you might hear me sniffling a little bit. Um, uh, so you may have noticed in the talk on the description, there was a small change in the description of the talk. It's still next-gen prompt engineering, but it turns out that this talk is going to be about a lot more than that. And it's really about code generation, prompt generation, and generally problem solving using large language models in an automated way. So what a year. I know that probably triggers a lot of things for different people, but it's been a crazy year for AI. Last year and even now, there's been a lot of excitement. I would say it's the excitement. Oh, you guys hear me? Okay. I would say the excitement has become now becoming more of it's getting mixed with a little bit of fear as well, and I want to kind of address that as well. But it started out with excitement, and it's usually how it starts with most organizations. You know, a lot of folks, they're looking online and they're seeing, I don't know who reads the newspaper, but they're looking online and they're seeing all kinds of articles about robots, AI, are they taking our jobs? And then, of course, you get this kind of cover, and after a while, everything these people say suddenly becomes the gospel at whatever organization you work for. So everyone starts out with big dreams, wanting to do stuff with AI. Companies dream of using AI for basically everything. We'll replace our customer service. We'll have developers that will be AI coders. We'll have AI product people. We'll have in fact, our whole business will be AI. In fact, you know what? Maybe we'll just rename the business to whatever we were doing, and then we'll put AI, and in everyone's title suddenly has AI in it as well. And leadership gets inspired by big talks from industry leaders like Sam Altman. And you know, that's the overall feeling is we got to get on this train. It's the way of the future. And it really is, but I think that there's a lot of it is not really rooted in actual knowledge of what these systems can do and why what we do is actually really important as well. It's also, a lot of it's rooted in just the hype. I mean, what people are talking about. Everywhere you turn around, people are talking about AI is going to do this and AI is going to do that. So, of course, everybody's organization is in constant meetings about AI. They're having war rooms and groups talking about AI, and you know, it's warranted. It actually really is important. So, of course, this always falls on the engineers. At the end of the day, we've got to build stuff. So everyone's in a room talking about all the great things it can do, and then it's like, well, let's make something. And so, of course, what does the natural engineer do? They start looking at everything. They start looking at large language models. Maybe before that, they even start looking at how neural networks work. They start seeing if they can train their own neural networks. They start looking at fine-tuning. They start looking at embeddings, classification. They start looking at statistics if they don't have a background in that. And they look at all the models and all the different tools that they can use. And it's just a lot. And everyone wants to do something now. And that's generally how we feel, especially when it's like, okay, well, what can we do next week, right? And so what do we end up doing? We end up sort of settling on the practical frontier models because they work. You can just get an account, go on OpenAI, get an API key, and you can start coding. You learn about tool calling, you learn about embeddings, you learn about RAG, you learn about all kinds of useful things, and you start making things. Of course, people look into Claude. That seems really cool, so maybe we can switch out models. Okay, maybe I need a framework. You start looking at LangChain. And of course, that dolphin shows up, and people are wondering, what's that dolphin about? And then, of course, OpenAI releases o1, and it's like, okay, well, what about these reasoning models? How does that work? How does that change things? And then you've got 3.7 Sonnet, and it kind of seems to do lots of interesting, lots of good work around coding and problem solving. And it's expensive. And then DeepSeek R1 comes in and says, okay, well, actually, anything you can do, I can do better. And it's free. And so people start looking at the statistics, and it looks really amazing, but then what does it mean to us? So it's time to start building. What do? We pull out LangChain or Light LLM. We start doing tool calling, RAG, like I mentioned before. We look at a lot of the different tools, and we start getting early results. This is where the excitement happens as an engineer. We start doing demos. We create a little AI assistant. We plug it into some data from our organizations, and things just sort of work. It's kind of magic, actually. It's really amazing. Why it works, no one can tell you, but it works. You just put a prompt in, you put some data in, and it seems to come back with the answer, sort of, and sometimes better than what you expected most of the time. But then sometimes you get stuff like this. Wait, I thought we made 13 million, or the forecast was 13 million, not 12.4. Where'd that come from? Now, of course, everyone sees all the output and is really excited. The organization's excited to actually keep building. But the engineer inside of us, the engineer who's actually working on this, inside our heads, we're thinking, that was wrong. That answer was wrong. And now I have to kind of do something about it. I don't know what to do about it, though. So it's time to start thinking about releasing a product. And then the engineer's thinking, how do I know if this is even going to work? Well, QA will find the problems, right? You just throw it over to QA. They're going to run some tests. And we did it. We released our part. They're going to test it. And you know, they'll make sure it's OK. But just put something together to get people excited, because there's just so much pressure to build things with large language models. So this is what we feel. So we start to abandon our principles about verification, about testing. We start to kind of move away from that and just sort of trust things, because it seems to work most of the time. But something's amiss. And we start running things on our own, and we start asking other interesting questions. And we start discovering, wait, there's no membership program. Where did it come up with that? Wait, we don't have patents. Why is it talking about patents? So of course, with all the big dreams that everyone has about, organizations have about building all these interesting things with AI, what ends up happening a lot, and this is what we've noticed at Singtree, is a lot of people end up settling on, why don't we just build a chatbot? Now, why do chatbots work? The reason why they kind of work is because generally, chatbots are, the interfaces with humans. And the large language model has been trained on mostly human input, human text, of course code as well. And so what's great about a chatbot is the user gets to fix the errors. The user chats with the chatbot, and it says, oh, that's actually not right. Can you explain this or explain that? And they're sort of correcting the problem. But if you just build chatbots, it's actually a pretty limited use of large language model. So of course, the engineer is pretty frustrated. You know, I thought I could build all these things, but now I'm just building a chatbot. So let's talk about what prompt engineering actually is. So, you see all the errors, you see all the problems, and you start thinking, I can fix this, right? I can do this. So naturally, the engineer creates a prompt. The large language model processes the prompt. The model generates output. The engineer evaluates quality. Sometimes the customer or sometimes someone in the company evaluates quality because they're playing around with it, and they say, hey, I entered this thing, and I entered this input, and then this happened. What's going on? Can you fix it? And of course, they try it. The engineer tries it on their own, and it doesn't do the same thing. The engineer, if they can see it, they'll identify issues. They'll try to judge the output. And after that judgment of the output to determine, okay, this output is more or less accurate. If there is a problem with it, the engineer modifies the prompt. That's what we do. We start kind of monkeying around with the prompt. We add stuff to the prompt. We just start adding lines to it. And if we wanted to think a little bit harder about a problem, we use things like chain of thought reasoning. Think step by step. If we wanted to never do something, we'll put in all caps, never do this, and hope that it works. And we start to ask ourselves, is prompt engineering the new coding? You hear about people talking about that. Is prompt engineering coding? Is this the way we're going to do things in the future? But as an engineer, I think anyone who's worked on this can probably understand this. It feels like when you're doing it this way, you're just chasing a ghost. You're actually not really solving anything. All you're doing is you're sort of trying to influence this thing that you don't even understand. You're just putting text into this prompt and hoping that it comes back with better answers. And even the people who created the models could not tell you why it answers the way that it does when in very specific cases, because no one actually understands what's really going on in the model. It's not a program. I mean, you could say it's a program, but we'll get into that in a second. So it just feels wrong. But we do it because it's working, kind of. It's kind of magic at the same time. And then we mess with it, and guess what? It starts working. So you get it working, and what if you change the model? What if there's an announcement, and you've got to try the new model because the new model's better at certain things, and you've got a bunch of different prompts in your application, and you start changing things. You start manipulating the model. And when you do that, you start noticing that there are problems that start to pop up in your application. It doesn't work the same way. Maybe it works most of the time, but then there are situations where it doesn't work, where it used to work. And no one can tell you why that is either. Because just because OpenAI releases or Anthropic releases a new version of their model, it doesn't mean, let's say it's 4 and then 4.0, it doesn't mean that 4.0 is backwards compatible. It's not the same thing. It's a completely different model. And even if it was built on the same model, it's been retrained, or it's been fine-tuned, or something like that. It's been messed with internally, and even the creators could not tell you why it does what it does. Let's say the requirements shift. You want to change things. How do you deal with this? And as the models, or as the prompts get more and more numerous, you end up with a lot of issues. And of course, you end up with cost concerns. What happens when the models aren't doing what you want them to do? What does everyone do? They just put a better model on it. Okay, we were using 4. We were using 3.5. Okay, no one's using 3.5. Okay, we were using 4, then we use 4.0, and then actually, you know what? Maybe we'll use Claude 3.5. Maybe we'll use 3.5 sometimes, and then we'll use 3.7 now. And generally, what will happen is people will just keep dialing up the cost on the model in order to get better performance, so they just kind of hide the problem away. But it doesn't actually make the problem go away. So is it really good enough to go to prod? That's the question I think we have to ask ourselves. So of course, you get an announcement from Google I/O. They're going to have the Google I/O conference, and then immediately OpenAI does Dev Day, just a day before the Google I/O conference, just to rain on their parade. And of course, that dolphin comes back again. So what's the problem? It's determinism versus non-determinism. When you are working on a computer program, you are working in a deterministic environment. You are building something that does what you expect it to do every single time. Generally, given the logic that you've put into it, you're writing a program. And I know for those who are into computability theory, they might say, well, models are not non-determined. They are deterministic. You can turn the temperature down. You can run it again, and it'll give you the same thing. But whenever you have this massive hundreds of billions of parameter neural network, and you throw an input into it, and it just goes, and outcomes and output, that's non-deterministic. Like, I don't care what you want, how you want to, for all intents and purposes, this is non-deterministic. And so this is why this feels wrong, because we're trying to create this deterministic process, or try to create this deterministic expectation around something that is inherently non-deterministic. So some features of determinism. You have a pretty inflexible interface. You have your code. Your code takes a specific type of input. The behavior is predictable. It's reproducible. Its logic flow can be traced. Testing can verify all possible paths. Classes of errors are fixable with specific changes. So what's nice about that is you can say, okay, I'm noticing that I'm getting this error when this happens. I can handle that case, and it handles the entire class of problems that are related to that particular error, and you can bank on that working out. And that's why we can solve problems so quickly in code, because after a few logical updates, it sort of all makes sense. It all sort of works. And we as engineers have complete control over that. Neural networks are a little different. You have these hyper-flexible interfaces. You can put anything in there for the most part, whatever types of things it's been trained on, but it's pretty flexible, especially large language models. But the results can vary as far as what you think should happen, depending on the input. And you can have similar inputs and get different results that sort of break what your logical understanding is, because it is not a logical system. And when you run it, it's sort of revealing like probabilistic results. You throw a bunch of stuff into it, and you expect the output to be over there, but it's over there. And you expect it to be over there, and it's over there. And so engineers have no control. We can only nudge through the inputs or retrain. So what do we do? So one of the things that we've told ourselves at Synctree is that we'll never fully trust a prompt, ever. We'll never write a prompt. We'll try to never write the prompt, actually, as well. There are some edge cases to that, but we try to never actually write the prompt. We prefer to use hard constraints, things that we expect, be very clear about those, and let statistics be our guide. And we'll rely on automatic verification, and we'll watch out for overfitting, because we're going to train prompts, and we're going to train code, and we're going to train configurations, and that's what we are going to try to do for everything that we build now. Instead of building things by hand, what if we could just train everything and use statistics to determine if the system actually works? So instead of treating an LLM like a computer program, like a deterministic system, let's treat it like what it is. It's a non-deterministic system. Let's run a bunch of inputs on the system and see what it comes out with, and get back a probability that it gives us what we want. So I showed the flowchart earlier about human-generated prompt engineering. So engineer creates a prompt, LLM processes the prompt, model generates the prompt, the engineer evaluates the quality, output is it acceptable or not, engineer modifies the prompt, and we just do this loop. But what if we can make that automatic? What if instead of manually going in and manipulating the prompt, adding another line to the prompt, what if we can make it do it on its own? So there are a lot of little decision-making processes in here. We've got the engineer, of course, typing something into the system. The engineer is judging the output, and the engineer identifies whether or not the output's good, and then the engineer modifies the prompt. So what if we could use large language models and a combination of different models, if we want to actually do that automatically? and then use statistics to determine how good the output actually is, or how good the prompt actually is. Because love it or hate it, the prompt is still our interface to the large language model, and love it or hate it, the large language model is pretty cool. It is pretty amazing what you can do with large language models. So this talk is not about this paper, but it is a lot of what we've done at Synctree has actually been very much influenced by some ideas from this paper. I highly recommend checking it out. It's called TextGrad. It's a great read. It'll really change your mind about how you think about prompt engineering and coding in general. It's actually it's a great paper. There's an open source project around it. I highly recommend checking it out. It's done by a bunch of students at Stanford, and really what it's about gradient descent, but with prompts. In fact, let me go back and I can show you. Whoops, I didn't mean to go that way. So this image that you see on the upper right-hand corner, actually, this describes, on the left, you'll see a diagram that describes backpropagation, and this is how neural networks are trained in general. And then on the right, there's sort of an analogous process that we just talked about. That this is kind of a more mathematical formalization of that idea, but basically, as you see on the right, you've got your loss, which is really what's wrong with the output, right? It's the error. And then you've got your loss over your response. How could the output have actually been improved? Like what would I have liked it to have said? And then we pass that, and this is what we do as humans actually. And then we pass that, what I would like the model to have, or what I would like the output to have been, we pass that to something that's evaluating the prompt. And there's a prompt evaluator that says, well, based on what I would have liked to have come out and what the prompt actually says, I think we could modify the prompt in this way. So it's kind of like backpropagation. It is like, in a way, it's like gradient descent, actually, if you actually keep running it in a loop. So let's make something. Let's do some prompt generation from scratch. A lot of what we're doing does not involve TextGrad, but like I said, it's a great project. But I recommend people actually get in and try to do this yourselves. Try to start from scratch and build something. So let me switch over now. Let me check on time. Okay. So let's get started. So let's come up with well, I've already planned this, so of course I know what the problem's going to be. We'll create a very simple system that answers questions about an article. And the goal is for the questions or the answers to create a prompt such that the answers that come out of the large language model and prompt together will be only things that refer to the things that are in the article. And we want to do this as a general thing. We're not going to say specifically for our particular type of article. It's just going to be any kind of article. So, given internet connection, I may end up walking through code rather than running, but we'll see how it happens. So let's get started. So the first thing I want to do is I want to generate an article. So let's start with that. So, excuse me? Oh, I'm sorry. Let's. Oh man. Is that good? I wonder if I could brighten it. Let's see. Is it going to do it? Yeah, the screen's resolution isn't great. Okay. Okay, let's try this. Yeah, it's going to really throw off our, you know, how everything lines up, but we'll try. All right. So I'm going to generate an article. I'm going to just create a simple Python function. It takes in a topic. It's going to return a string, and it's going to we'll let Copilot guide us as well. Why not? Given a topic, generate an article, sure, and then oops, sorry. All right, what's up? Okay, here we go. All right. So I'm going to create a little prompt, and the way it's going to work is it's going to say, yeah, sure, that sounds pretty good. Generate an article. Okay. Markdown format. How about each paragraph will need to be, prefixed by a section. Yeah, that's good enough. And then we'll return. I have this little function called simple prompt, so mostly for this talk, so that we can avoid a lot of the inputs. Oh, you know what? I'm going to go ahead and create the article model, like a little string that represents our article model. And I'm going to use GPT 4.0 mini, okay? All right, simple, yeah? And then what I'm going to do is I'm going to just log this thing out. So I'm going to say generate an article about, let's say, the Scale conference. Okay. All right, simple enough. So we'll start off with some articles. Let's give this a run. Hold on. Keeping some notes here so I don't get off track. All right. All right. All right. Easy enough. Up. Hold on. Let's try that again. It's throwing off my screen here. Let me just try to make this bigger so you can see. Okay. All right. So there's an article. Easy enough. All right. So let's take a look at. Let's take a look at what to do next. So now I want to create some kind of program that will take the article and a question and will answer the question, right? That's how we start usually, this kind of thing. So this should be pretty easy, right? We just answer question, prompt, a question, and an article. All right, given a question and an article. Sure, generate an answer. That's good. That's a good enough doc string, I think. And we'll just return simple prompt. And you know what? I should do. Copilot knows I've done this before, so it's kind of guessing. We'll use 4.0 mini as well for the answer model. Yeah, let me switch. I'll try to switch around. I didn't expect the resolution to be this bad. Okay, all right, and let's see. Um, oh, I'm like, what am I doing here? Okay, hold on a second. All right, let's try again. Let's do it like this. And you know what, I'm going to take this off because I can pass its parameters, and then I'll just do answer model. Yeah, looks about right. All right. Let's remove that. It's guessing. Okay, there we go. Yeah, okay, yeah, sorry, okay. I might just abandon this live demo just because it's because of the text and the screen situation. But basically what I'm doing is I'm essentially creating a, I'm generating an article, right? So generate an article about the Scale conference. Actually, that's here. And then what I'm going to do is I'm going to answer a question about that article. Okay. All right. Sorry, say again? Oh my gosh. Yes, I think yeah, it's this, because I can't see, Marilyn. All right, let's try this again. Thank you, by the way. I think I'm going to do it like this too, because why not? All right. All right. All right, let's see how I get back to my terminal. All right, so let's give this a run. What's that, Mark? Thank you for that. Good to see you again, by the way. All right, here we go. Okay. So I have a couple of recordings from the previous runs, just because I was having some internet connection issues as well. So, what is a Scale conference? Answers the question. Tell me about the latest iPhone. And I'm sorry I can't provide information about the latest iPhone. Now, what would happen if we change the answer model to something else? Let's use, I believe it's called, let's see, what do I have it labeled as? Hold on, I have a note on what I'm labeling it as. Yeah, 2.5. So Quinn is a large language model that was developed by Alibaba, and they have it actually performs pretty well. And there are some distillations from from DeepSeek as well, and it actually turns out to be a nice little tiny model, but it hallucinates a lot. In fact, let me show you. If you've never run Olama before, hard to see here, but all right. So this is a 1.5 billion parameter large language model. Runs on my laptop. I can call it as many times as I want. I don't have to pay for it, and I can talk to it, similar to how I might talk to GPT-4o. It doesn't support tool calling, but you can kind of make it work with tool calling if you do your own thing. But it doesn't have that built in. But it may not be good for. So as you see, it doesn't know what the scale conference is, but maybe we could tell it about it, and it would be able to answer questions. Okay. So I'm going to jump ahead a little bit. Give me a second. I'm going to just speed this up and kind of prevent some of the issues. I'm going to go ahead and jump ahead and show you. Give me a second. I have a backup of the original. I'm going to just do this because I think it would be more, given how hard it is to see everything. I'm going to show you guys what it looks like. And we'll just review the code and I can just talk through it. It's probably better. All right, so this is actually the completed version. I'm just review this with you, and then we'll actually run parts of it. Okay, so we're answering questions, right, as we saw earlier. And then what we wanted to do is we wanted to evaluate the answer. One of the things that we noticed is that when we ask Quinn questions, and I believe we have a run here that I can share with you. Whoops, hold on a second. Here we go. Jeez. Okay, so let me kind of show you what's going on here. So we created the answer question function. We have our prompt, we have our answer model, and what we did was we went through our collection of answers and we decided to start to evaluate the responses, because what we noticed was that Quinn was actually giving us back hallucinations. It was making stuff up. We asked it about the iPhone, and it was just making things up about iPhone sales when we were talking about the Scale conference. So we wanted to try to figure out how could we use the Quinn model still, because it's cheaper, it's really fast, I could run it locally, and it's just a good example of a really cheap, not very good model. How could we focus it to do something useful? So, and also exercise this process that we talked about of text gradients and backpropagation. So we created a pydantic model that essentially describes an evaluation that we would expect from a large language model. Now, in order to do this, you're going to need to run this on a model that can support tool calling and a model that can actually adhere to a schema. So usually, the models that are going to be doing the judgment of outputs, that are going to be editing prompts, are going to be more on the frontier model side of things. But ideally, that's really mostly where you'll be using those. You can also use this process for a frontier model to judge itself, to judge another instance of itself and improve its own prompts. So it doesn't mean that it has to be teaching a weaker model, but we're using this as really an illustration here. And then we tell it about this concept of error. What I want you to do is I'm going to give you, for a question and an answer, I want you to give me the error, and I want you to give me the reasoning for the error. So remember, that was that loss function that we talked about earlier, where we look at the output of the model and we judge it. This is what a human would do. A human's going to look at the output of the model and they're going to say, oh, this could have been better in this way. So this is the evaluation model, and then we have a function to evaluate the answers, and it's actually quite simple. Hold on. So here, if I can show you a little bit there. Okay. So evaluating models or evaluating the response is actually really, really easy. Now, there are little tricks when you get more complex and you start doing code generation, things like that. But for the most part, it's pretty straightforward. You just say, hey, given my problem and this solution, tell me what you think about how good the solution is, and give me your reasoning, and judge between 0 and 1. And believe it or not, actually, that concept is pretty well understood by most frontier models. And so we implement this evaluate answers function, and then when we implement evaluate answers, we get this back. And I'll show you, because we have a rerun of it. Okay, here you go. So in this situation, what we're doing is we're throwing a bunch of questions with an article about the scale conference to our model. This model is Quinn, the Quinn 2.5, 1.5 billion parameter model. And then we take the output of Quinn, and now we're judging the output with 4.0. And so you can see it answers a question about scale, and it says, hey, this is perfectly fine, and its reasoning is the answer accurately reflects the information provided, and so on. But then we ask it about the latest iPhone. And when we ask it about the latest iPhone, it says, well, the most up-to-date information on the latest iPhone is that they're part of the 2023 lineup, however, specific details, blah, 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 blah. And I specifically told the model, or told the prompt, told the model through the prompt, I specifically said, don't make up stuff. Just give me back things that are based on the article that I provided. So 4.0 takes a look at that and says, that's wrong. So the error is 1. And since the error is 1, of course it's going to give a reason, and the reason is the question about the latest iPhone cannot be answered based on the article, which is solely focused on the scale conference and does not contain any information. So now we have our loss. So what we're holding here on the right is the output of the loss function. Evaluation is basically our loss function. So what do we do? So what do we do with our loss function, or with our loss? Okay, here we go. We want to try to start adjusting the prompt. So we take our loss, our evaluation, we pass it into another call to the large language model. We say, given this, what our goals are, given what we saw happen, tell me how we could improve our prompt. And I want to say the other thing about this whole process is that data is your friend. You want to be able to do this a lot. You can't expect it to just sort of work after 1 or 2 tries. You're going to have to pour a ton of data into it, and sometimes what's really useful is synthetic data. One of the things that we've been doing is we've been sort of making up data based on data that we already have. So we'll take a bunch of, like a corpus of similar data, and then we'll just generate a bunch of data similar to that, and then we'll use that as feeder data into our training process. So here's the adjustment model, or adjustment. This is the adjustment prompt that calls the model that we're using for adjustment. And really, it's quite simple. This is a prompt with the highest score so far. We just do that because that way it has a reference of how good it's done before, and just in case it starts going off the rails, it can kind of like pull itself back. We've noticed that that's been a very useful thing to have that in context. So given the following prompt, adjust the prompt to fix the following errors. And the errors are the losses that we collected in the evaluation. Do not overfit to specific errors in the example. So overfitting is really about, if you're training a model traditionally, if your model is just sort of mimicking the outputs of your training data, or mimicking the expectations of your training data and is not generalizing, then you're basically overfitting. So we don't want to overfit, because, so what does overfitting look like here? What overfitting looks like is a bunch of data that's going into your prompt with special cases for everything that we've seen before. And we've actually seen that before. So we've noticed that if we tell the model, don't overfit, we're going to try to generalize the problem, it actually does work quite well. And by the way, you might say, well, aren't you like writing a prompt to write a prompt? And you said don't write prompts. Yeah, I am actually. I am writing a prompt to write a prompt. But actually what we do internally is we train these too. I'm just showing you how to do it manually, and just to kind of get started. Okay, so we pass it through and we get a prompt adjustment. And I think that, let's see, I believe, let me see if I have a rerun of this one as well. I can show you. Okay. Actually, this is the main run, and I'll show you that. So in order for this to work, we're going to need a lot of topics. We're going to need a lot of questions. So we have a question generator, which is similar, you know, just pass an article in, give me some questions. It's really convenient for these kinds of things to use a frontier model where you can do tool calling, and also where it will adhere to a schema. It just makes everything so much easier. But don't let that dissuade you from using weaker models or models that are non-frontier models. With tools like this, you can technically use those models. Just I wouldn't use it for training. We found that it's just not practical. Although DeepSeek R1, the 30 billion parameter model, we did run those. We ran that model on RunPod, and it worked really, really well actually. And we swapped it out for Claude. Not the latest one, but the one previous. So there are some exceptions to that. DeepSeek R1 is actually pretty nice. So anyway, so we generate questions, we generate topics, or we got a bunch of topics, we're going to generate a bunch of articles, and this is our evaluation. Okay, and then here's our logic right here. So this is the loop. What we're seeing on the screen right now is that loop where I showed the diagram where the engineer is making changes or reading the output of the model, and then it's going to make change. It's going to judge and then make changes to the prompt, and it's going to go round and round until it gets it right. Well, this loop is basically that. This is that manual loop now done automatically, and just a quick overview of what's going on here. So we evaluate. Just kind of to create a baseline. We evaluate where we're at. The evaluations, again, that's the loss. That's, you know, here's what's wrong with the data. Here's what's wrong with the output. Here's the score. And then we then go through and we run this in a cycle until we've hit our error goal. And what we've been doing is we're going to just get the worst 2 errors, because we could pass like all the errors in, but we found practically you can optimize this process by focusing on specific errors. Otherwise, the model starts to try to address too many things at once. Kind of like a human being, right? Like if we were to try to fix a coding problem and you were given a ton of errors, a ton of different problems, it's actually, what we're going to do naturally is we're going to focus on one at a time. So, and I'll talk more about that later because we're going to get into code generation as well in a bit. Let me check on time. Okay, I'm going to go a little faster now. Okay, so we adjust the prompt for errors, right? We collect all of our errors. We adjust the prompt for errors. We take our adjustment. We evaluate our adjustment to see how we've done so far. And then we do it again. And we just do this around and around until we get our final result. And I'll show you the output of that now. Okay. So this is that program that you see there running. Unfortunately, I'm not able to really show everything on the screen, but I'm going to try to show you at least what the final result here. And so what we're seeing here on the left is okay, so it's adjusting for errors. I made several key changes to address the identified errors. I've added stronger language about not filling in gaps with general knowledge, which addresses errors. I've added a guideline to explicitly state when a person or event or a concept mentioned is not in the article. It's just doing all the stuff that we would have done manually. It's actually doing it. It's doing it automatically with the model. And it's going to keep trying. And it's going to try a lot faster than we can. So we might be able to get to the heart of, well, there is no heart of the problem. It's just this massive LLM. So we might get to what we think is a working system faster than this system can, as far as, or with less iterations, but not faster. Because we can just run this, go have a coffee, and come back, and it'll be done. So finally, we ended up getting to 90%. Let me just kind of, this is not helping you guys read this, I know. I'm sorry. I'm just trying to see it on my side here. Okay, and then we have our final result, and it's kind of hard to see, but unfortunately, everything is sort of squished. But it's basically created a new prompt, and it's created a bunch of requirements for that prompt below it. Oh, hold on. Just another run here. Let's go ahead and run through the whole thing. And you can see some of the things that it's doing. It's giving guidelines, important guidelines, include this information. And if you've ever worked with large language models and actually tried to like make things for production, everyone who starts out starts kind of doing this stuff by hand. And in this case, we're able to just sort of generate this on the fly. And this is a very rudimentary example. There are better systems for doing this, which we'll talk about in a second. But I wanted to just show how you'd be able to do this from scratch. Okay, and finally, we get to over 90%. So we started out pretty weak. I think it was, in the beginning, it was closer to 60%. And now using Quinn, we're able to, or using dynamic prompt generation or automatic prompt generation, right, we're able to get Quinn to behave in general for this particular task at over 90%. So let's switch gears back to the presentation here. So the traditional problem-solving process has been you pass a problem to a human being evaluates the problem, the human creates a solution to the problem, the solution is tested, sometimes automatic, sometimes the human just tests it, the outputs are produced, the human evaluates the output, and it processes the updates, just like we saw before, but now this is more generalized to any kind of problem, not just a prompt. Because the process that we just talked about, that we just went through, actually applies to many classes of problems. And in theory, I mean, most problems in general can be solved using this process.
10 minutes.
Thank you. So some people have probably heard intelligence is the log of compute. This is like a new concept. Intelligence is the log of compute. So if you pour compute in, you get intelligence out. And in the past, humans have had a monopoly on intelligence, and now for the first time, we're able to get intelligence out of a machine. And I think this is a pretty important moment. Now, of course, when did things get so flat that it doesn't really matter anymore, and we really still need the humans, and we still do actually. But generally, this is the way we are starting to solve problems with many of the projects that we're doing. We're looking at a way to create self-improving systems. And that doesn't stop at prompt engineering. It also is for coding, and we're also looking at how can a product team actually self-improve as well, or a product in general self-improve, using automatic user feedback and doing the exact same process with code generation, configuration management, or configuration updates, and so on. So is this really intelligence? I think there have been a lot of statements, especially naysayers. This isn't really intelligence. It's just predicting the next token. It's not trained like a human being. It's not really intelligence. For all intents and purposes, we're extracting intelligence. It's clear to us because think about code. Code is a manifestation of intelligence. And we can actually generate code, and code that works well, and in some cases, code that is more thorough than the code that we would write. So we are working on an open source project right now that we are going to release at the end of Scale called the Automatron Use Solver project. And really what Use Solver is all about is being able to do all the stuff that we just showed, or I tried to show, unfortunately, sorry, in that manual implementation of prompt generation, but actually kind of build in all the tricks and do this in a way that's very easy for a developer, a Python developer, and eventually other languages can bring in. And so I'm going to show that now. I won't have time to do a full coding demo where I'm going to code it because, as we can see, there are some issues with that. But I will show you some examples of things we've solved just recently. And so what is USolver for? Prompt engineering, prompt generation, automated QA testing, data lake, data warehouse systems, generating SQL, generating an entire data lake pipeline. All of these kinds of, that world of things is actually, that world, the data warehouse, data lake, it's actually a really convenient world for tools like this we found. Web scraping and data extraction, data transformations, and inference cost optimization. So if I want to use a smaller model that costs less to do a very specific job, it's not going to do everything, but it's going to do one thing for me, I could use Solver to do this. I'm going to show you here. I'm going to show briefly, I'm going to show briefly the screen for the Solver. So one of the things we wanted to do for the talk was build a scraper that could scrape all of the talks on the Scale website, and also could scrape all the speakers that are at the conference. And so anyone could do this. Anyone here probably can pop up beautiful soup and hack away at this, but we didn't want to write it. We started our code like this. The USolver decorator is pulled out from this, and I can show you but when we show it this way, we don't show the decorator actually in the solutions. The way the decorator works is at runtime, if there is a solution, it takes the best solution that's available for that particular function at runtime, and it swaps it into the code, into the runtime environment. And when you're calling it, you're actually, so if I call parse conference speaker, I'm going to call the code-generated version of it that was generated by our solution pipeline. So we start out, and it does nothing good. This is what I wrote. I wrote parse speaker HTML and return a speaker object. That's all I told it. And I gave it a schema. That was another important thing. I gave it a schema, and we could review that. And if anyone wants to review it with me afterwards, I'll be happy to show you. And then it starts working on it. And as it's working on it, it's telling you what it's doing. So in this epic, it implemented the function. And when it implemented the function, it was able to, it got lucky. And usually this doesn't work out this well. I think the Scale website's really easy to parse. That's why it happened. But it was able to get 99.1% immediately. But there were problems. So let's look at what it generated. And if you're looking at this code, I didn't create a framework for scraping. I just said solve this problem, and I gave it a schema. And if you're looking at this code, 3 years ago, if I told you, hey, I got this code, I have this code, could you take a look at it? Would you have guessed that a human, or that a machine wrote the code? Probably not. And so for those who say this isn't intelligence, I mean, come on, like, it's pretty clear. I put compute in, and I got like what clearly looked like intelligence out, or a result of intelligence out. And it keeps going. Okay, it's been updated to handle test cases. It would be nice to probably have a diff here, but basically it talks about what it's doing. It's been updated to handle test cases where the company field is empty and so on. And as it's going, it's also documenting the newly discovered requirements. Because a lot of times, as you know as engineers, you get requirements, and those requirements are not always clear. Well, this system actually it's discovering the requirements by looking at what requirements are sort of implicit based on the problems that it's finding as it goes, and it documents that. And it turns out that this is actually a very good way to solve problems, and so that's kind of part of some of the tricks that we've added to this. And then finally, it gets to 100%. And we also parsed all the presentations, and we did the exact same thing. So, back to the talk. Okay, I think we're just about wrapped up now. So where do we go from here? I would say a lot of people are saying, well, is this going to be the end of software engineering as we know it? Are the large language models coming for our jobs? Yes and no. I think that this is really about, one, we shouldn't abandon what we know. We should try to build reliable systems. I think that we should shift from building components and move into building systems that are self-improving. We have to be the ones who build those kinds of things, and not just sort of build the one-off interface or the one-off script. Let the models do that. That's what they do best. And we should be building the systems that self-improve so that organizations can get a leg up by creating an engine, a product engine, instead of a product team that only turns when there's manual intervention. The heart of all this, the way you make this work, is verification. So if you have a way to verify your problem, you're almost there. All you need is input data. And in a system like this, you'll basically be able to solve your problem automatically. So whenever if you're struggling with, like, how would I use this for my problem? Just think, how do I verify my solution? And how do I get data? Synthetic data or actual data is okay. And I think in general, have to take a more machine learning mindset to everything that we do. Now, one would say, well, but you need less engineers to do a lot of the work that's being done because of large language models. I think what's going to happen is people are going to realize that they can build things very easily now. And so because of that, the expectation is going to be, well, build everything. Solve every problem. Every single thing that you see as a problem, I think the expectation is going to be, well, just solve it. There's very little risk. You might as well just build something for it. Why not? Even if a few people use it, so what? Just build it. And I think this is going to happen more and more until the point where everyone feels comfortable with the idea that they can create software. But what that means is real engineers are going to be needed in order to build these kinds of systems, and also to repair those problems when people just throw, vibe coding and talk to a large language model and have it like generate crap. Anyway, that's it. Thank you. I know I went over. Were there any questions? I could take a couple questions.
Thank you. The evaluator in the demonstration, you talked about that not only does it need to be able to call tools, but you need to give it a schema.
Yes.
That's a schema of basically how you want the result to be structured?
Yes, basically. A JSON schema, ideally.
Okay.
Yep.
Thank you.
In one of your slides on that text grad paper from Stanford, you showed the gradient descent and the backward propagation.
Yes.
The reason why recurrent neural work and LSTM failed or didn't do well is because of the vanishing gradient descent problem. And that's what the Google solved with the attention is all you need at paper with the solving KV problem. So did that, I didn't read that paper. Did that paper going back and looking at the backward propagation?
No, are you saying, so let me make sure I understand. You're saying that the attention is all you need paper addresses the vanishing gradient problem.
Yes.
And you're saying, is there an analogous problem in the text grad context, and how would that be solved?
No, no.
Oh.
Did they go back and look at the gradient descent?
Did who go back?
Yeah, this text grad paper.
Did they go back and look at the vanishing gradient problem?
Yeah, yeah.
No, I don't think that that applied in this case.
Okay.
So it's interesting thing about the text grad concept. It is not a strict mapping onto a traditional gradient descent. It's more of a high level sort of pattern, if you will, that is very much borrowed from the concept of gradient descent and back propagation. So a lot of the issues are not sort of addressed in the same way. So if you actually, one of the things we found was, you know, in the beginning of the paper, it talks a lot about how this is the same thing as basically autograd, and you're basically doing gradient descent. But it's actually quite different. And when you actually start to dig in, you discover that there are lots of little tricks that only seem to apply to text gradients. And so that's actually why we decided to not, we were using TextGrad for a while, but we noticed that it's quite limited because there's a lot more flexibility in what you can do. And we decided to not use it and build something different because we found that this concept is actually much more generalizable to other types of problems, and we prefer to.
Thank you.